prove the series n plus 2 factorial over n to the n is convergent. This is just another ratio test. This is the formula for the ratio test. So now we plug in an plus 1 actually turns this into n plus 3 factorial. So I got to put the limit here first. N plus 3 factorial over n plus 1 to the n plus 1 times the inverse of this, n to the n plus 2 factorial. Expanded, this is equal to limit of n to the infinity n plus 3 n plus 2 factorial. You decrease this by 1 because this is n plus 3, the term that you already got by adding it to 3. So you go to the next integer down to resume the factorial. N plus 1 to the 1 is n plus 1, and then n to the n. Because you're already dealt with n plus 1, so all you got left there is n. And then you have n to the n on top, and then n plus 2 factorial on the bottom. Cancel out like terms, and you're left with limit n to infinity, the absolute value of n plus 3 over n plus 1. Now, these are both the same degree and term, so you could divide this fraction by n, which will give you, and the reason why you want to do that is because your limit is going to infinity, but we'll get to that in a second. Divide n by n, you get 1 over 1 plus 3 to the n over 1 to the n. Now, when you take n to infinity, these two terms, the limit of those two terms approaches 0. So what you're actually end up with is 1 over 1. Okay, I actually made a mistake. This should be n plus 1 to the n. So this doesn't cancel out at all. But still divide those parts of the fraction by n as well. 1 to the n is just 1. Because no matter what value of n you got, it's going to be 1 no matter what. And on the denominator, you got 1 plus 1 over n to the n. And this fraction here is the same thing as 1 over e. That's the definition of the Euler's term e. And then that's being multiplied by 1 over 1, as I told you earlier. And since 1 over e is less than 1, by the ratio test, the series is convergent. We got this half of the 9, and then we got 2 more problems after this, so it'll probably take 2 hours. Find the Maclaurin series of f of x equals cosine of x. Right, the first 5 non-zero terms. Before we do this, however, we need to find the series of x, because cosine of x is equal to the derivative of sine x. So the series of, writing out the Maclaurin series in general, we get f to the n of the 0th term over n factorial over equal to f of 0 plus f prime 0 over 1 factorial plus f double prime 0 2 factorial, and so on. X squared times x squared, and so on. So now we need to plug in sine x. Where sine of 0 would be 0 plus cosine, because the prime of sine is cosine, derivative of sine is cosine. Cosine 0 over 1 factorial is times x is just 1 over 1 times x is x. Plus, actually, minus sine of 0 is again 0. And let's just do one more term. Plus, in this case, still minus cosine 0 over 3 factorial x squared, which is 1 over 3 factorial, where it's x to the 3rd over 3 factorial. And if you were to continue this pattern, it'd alternate to x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. And if you take the derivative of this, because the derivative of cosine, because the derivative of sine is cosine, the series of cosine is written out is equal to 1 minus I'll do the first one and then I'll skip the other ones. 3x squared over 3 factorial. 3 times 2 is 6, but you could just cancel out the 3's and just resume from 2 factorial. Then the derivative of this would be x to the 4th over 4 factorial by the same logic with the 5's, minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, and so on. And if you can figure out what series this is, this would be the series that starts with n equals 0 to infinity, where it's alternating, so it's -1 to the n. Then you have x on the numerator, 2 times whatever place in the series you're in, over 2 times the place in the series you're in factorial. And that's the series. That's the Maclaurin series for cosine x. Number 10, it asks us to find the arc length of the cardioid x